This video is an overview of ILM 302A, Introduction to Three-Phase Induction Motors, Objective 1. One of the first things you'll see in this module are some definitions that you need to know. One of the first definitions is torque. And when a motor turns, it creates a rotational force called torque. So whenever a motor is operating, it is producing torque. Counter torque always opposes torque. And counter torque is what we have whenever a load is added to a motor. A load will provide counter torque to the motor and oppose the torque that the motor is creating. And one thing that's always important to remember about counter torque or adding load to a motor is that when you add load to a three-phase motor, it will always slow down. Once you've added load and the motor has slowed down, it will draw more current to provide more torque to turn the bigger load that you have added at a slower speed. If we were to add more load, the motor would slow down some more to produce more torque to overcome the extra load or counter torque that's been added. And if we were to take load off the motor will require less torque to turn the load, and as the counter torque is taken off, the motor will speed up. As you take load off of a motor, it will cause the motor to speed up, reduce motor torque and current. From there, we look at a couple of torque formulas. And you're given a couple of formulas on page 4. And I think that when you're given two formulas like this, you don't need to memorize both of them. Both formulas use power. The only difference between the two formulas is one uses power in watts and one uses power in horsepower. And so I would suggest just memorizing the forms of one formula. I would suggest the one that just uses power in watts, because you can always convert horsepower to watts. And then you should be reasonably comfortable solving it for power, solving it for RPM. Hopefully you're fairly comfortable rearranging formulas that way. To give you a bit of practice with these formulas, here's a question you can use the formula for. You can pause the video here and solve this problem. The formula should be fairly straightforward to use. Either form. Again, I don't suggest memorizing all of the different forms. If you were to get asked a question where the motor torque is at half load instead of full load, half of load would require half the power of the motor, so you just need to use half the horsepower rating of the motor to solve this. In the end, you should see something like this. So torque should be fairly straightforward as long as you know the formula and can rearrange it fairly easily. One that isn't given here, that would be a good practice to do as well, is can you take this power formula equals torque times RPM over 9.55, can you convert it for RPM? Take a minute and see what you would get for that. What you should get is RPM equals power times 9.55 over torque. Another thing the module talks about in the first objective is motor efficiency, and the formula that we can use to find motor efficiency. And a motor has electrical losses and mechanical losses. The electrical losses are just like the losses a transformer has. A transformer has no moving parts, so it doesn't have mechanical losses, but a transformer has core losses and copper losses. And just like a transformer, a motor will have these losses as well. So the motor can have electrical losses and it can have mechanical losses. And mechanical losses are generally friction of the bearings in the motor, and bearing friction is a heat loss in the motor that makes it less efficient, and windage is a mechanical loss where a fan mounted on the motor will cause that motor to work a little bit harder and not produce any useful work from that. So it's a mechanical loss as well. These losses are almost always given to us in watts, and we can use the basic formula for figuring out efficiency to solve for motor efficiency. So the basic efficiency formula again is output over input, or output over output plus losses is the same thing as the input. So for a motor, that formula only changes to say it's motor output over motor input, or the output plus the losses. A little practice using this formula. You can stop the video here and take a couple minutes to solve this problem. Again, it should be fairly straightforward to solve if we find the watts output over the watts input. And whenever we see a rating on a motor, if it says 25 horsepower on the motor nameplate, that is always the output of the motor. And the input, of course, will be the output plus the losses. So in this case, the motor efficiency is 87%. So that's really all there is in Objective 1. A couple of formulas to know and a couple of definitions to be aware of.